So we looked at in the previous two videos about how to create threads, how to create an array of threads, and how interference happens, and basics of what is called concurrency, right? So the important thing to note here is what we are trying to do is multitasking, perform more than one task at a time. So in those examples, we had some print statements, and those print statements are basically getting executed by many threads, right? So many tasks are happening, in that sense. There is concurrency because, concurrency as in, many things happening at the same time. Uh, you see concurrency there because, those two lines, print hello world and print uh, bye world, these are the two lines that are basically getting interleaved, among different threads. So we created four threads, and we saw, how different threads are basically racing against each other to do print, one of the print statement at a time, and then one thread can be knocked out, and the other thread, you know, goes through those statements, and the second thread moves away, and then third thread gets to work on those two print statements, right? So several interacting code sequences are getting executed simultaneously. So that's what concurrency is. Many threads are able to make progress towards solving a problem. So that can happen if you have, let's say you have one processor. uh, there could be interleaving of code statements by a single processor, right? In one processor these days, we have multiple cores in one processor, so it's possible that these threads are executing on different cores of a processor. So this is called parallel execution. In reality, two processor cores can work at the same time, you know, do those print statement. Now everything is fine when there is no sharing of memory, but when there is sharing of memory, then there are some concurrency issues that we need to think about. It's like if you let two boys do the painting, and there is only one paper where the painting is being drawn, then if there is no so there should be some cooperation between these two boys, so that one boy does not interfere with other boys uh, painting work. So in many cases, like sharing that paper for painting, memory is also kind of scratch pad where your program uses to perform some to calculate some meaningful results, right? So the memory, um, we have to protect memory, shared memory, shared among different threads from interference, so that the behavior of the program is correct even when that program is run by many threads. There is concurrency in your program, right? So how to deal with all those concurrency related issues is what we are going to see next. So to motivate this part, let's assume that you have a variable in memory, let's say 12. This is an integer variable, uh, and this is stored, let's call it a counter. uh, it's stored somewhere in memory, and there are two threads, T1 and T2. If both T1 and T2 are trying to increment uh, the count, so uh, increment, the logic is counter plus plus, so whatever the value of counter is should get incremented by 1. So uh, if counter is a shared variable among two threads, and both threads are you know uh, concurrently trying to increment the counter variable, then the output is really undefined. So you expect, in the ideal case, that if two increment happen, the answer should be 14, right? 12 to 13 and 13 to 14. But that may not happen if the threads are interfering with each other. So that's what we want to see. Now understand, the concurrency problem. So this is the motivation. So in the book you will find a counter class. So in the slide you can see. So counter has a variable count. Initial value is 0, and the increment method basically adds 1 to it. And there is a get method to return whatever the count is, right? So this is the counter that we want to initialize, and call the increment method to change it. And we'll do that using one thread and then two threads. So this is the second class. This is demo one. What we do is create an object of counter class and then call increment 3 times, right? So the value of C, which is initially 0, should be incremented by 3 times. So what should get printed here? Yes, you are right. It is 3. So count is 3. Now this one was main thread, right? So only one thread was doing increment. Now we will add some threads. So we have an increase because we want to use threads. So we make a class increase and let it implement runnable so that it has a run method, and then it has instance variables count of type counter and amount. And we will see why we created this class. So when we create threads, we want to make sure that those two threads are sharing this counter, okay? And then only interference, we can work on interference, right? The shared variable is stored in counter, so it will basically hold a reference to, it will store a reference to whatever C comes here. And then amount, right? So whatever number you pass here, that many times it will do increment. So if you pass 10, then C will get incremented 10 times. And now you think of this as a multi-threaded program, right? So there could be more than one thread that are doing run concurrently, simultaneously. So the two threads, may race against each other to do the increment, right? So we saw increment is in counter class. Demo number 2 creates a thread, initializes counter like in the previous one. Instantiates increase and passes amount as 10,000, and it's also passing C, which is going to be to the increase constructor here. And this R is getting passed to the thread constructor, right? And then you say T dot start. So when you did say T dot start, then the run method starts getting executed, okay? And you print the count. So in this you expect 10,000 to be printed, but you see that 10,000 doesn't get printed. So you get output like this when you print count. And the reason is we forgot to add something. The hint is forget to wait. So there is a join statement required. So what happens is main thread is running, thread T is running, so two threads are running, right? Main thread instantiated counter, instantiated runnable object, and then instantiated the thread and starts running, right? That means it went to the run method. T, the thread that got created in the run method, it has to increment amount number of times. So what happened was returned main thread is displaying counter. So this display counter is the last line, println line. On the other hand, time is running down the y-axis in this direction. So time is passing, increasing, and even though thread T is active, main thread did not wait for it to finish the increment. So prior to counter becoming 10,000, it's displaying it. So that's why you get this variable number, and it's unpredictable. As you're running this program time and again, you're basically getting different answers, different value of count, because main is not waiting for this thread to finish, right? So it can basically do the print statement at any time. So hopefully this explains why we get different counter values and why now we need the join statement. So this is a very good example to explain with or without join what's the difference, right? So this is a wait statement. Now demo number 4 creates two more threads, right? So there is a main thread, but main thread creates two new threads, okay, T1 and T2. Each thread should basically increment counter by 5,000, okay? So what you expect? You expect basically, counter being executed in total 10,000 times. You start the thread and the main thread is waiting for T1 and T2 to finish. And after the threads are done, you want to print the value of counter, right? So whatever it contains. And this is a shared memory exercise because the same C is going to both the threads, right? It's the same, you're passing the reference. So the threads, when they're running, they're incrementing the same count instance variable inside counter, okay? Now here is where thread interference will happen. Some of the increments will get affected by the fact that other threads are also trying to do increment at the same time. So threads accessing memory at the same time simultaneously may lead to problems. So you expect 10,000, but you get a different number, okay? So how to fix this problem? We want threads to increment the variable count in such a manner that we get 10,000 reliably. We don't want to lose any count. We don't want the answer to be less than 10,000. So what do we do? So we will look at how to fix this problem, but um, there is some explanation, some details about why this happens. So here it is. So incrementing a variable by one, incrementing count by one, there are three steps here. So the first step is you obtain the value of the counter, which is 12, and then you increment it and then you store it back to the memory. So the first step is basically reading the variable from memory to processor, and then processor increments the value, and then whatever the answer is, it has to be written back to the memory, right? So one line of count plus plus gets broken down into three lines: uh, obtain, increment, and store. So what happens is, when thread T1 is trying to increment, thread 2 T2 is also trying to increment, right? They are working simultaneously. So interleaving of the steps can happen. So this is one scenario that is being shown here. So thread number 1, T1, gets reads the value to the processor, and in step number 2, instead of this increment happening, the control goes to thread number 2. So thread number 2 is reading the value from memory to the processor, right? So it also reads 12. Now when thread number 1 increments the value to 13, thread number 2 is oblivious to the fact that the value has been incremented to 13. Why? Because it read the value prior to thread number 1 incrementing it, right? So we see the problem here. Thread number 2 is working on a stale value, old value of counter. So then thread number 1 stores it, and now the memory is updated. The memory contains 13, but then in step number 5, thread 2 also updates 12 to 13. So both are basically the answer is 13. The answer ideally the answer should have been 14, because two increments happen, right? Increment here and increment here. But since there was interleaving of the steps among these two threads, between these two threads, we didn't get 14, we got 13. So this is just showing how one increment could have interfered, right? Increment by thread number 1 and increment by thread number 2. But if you look at the code, this interleaving um, or interference can happen amount number of times. So thread number 1 is trying to increment it by 5,000 times, and thread number 2 is trying to increment it by 5,000 times. So there is a lot of opportunity for interference to happen, and that's why you get unpredictable results. Okay, yeah, so think about it. And I have a program that also shows this behavior here. It's called demo 4. So I run this. I get 7,000. It's the same program. I expect 10,000 if there was no interference between the threads. If a thread is able to run those obtain, increment, and store, those three things as one step. If that was possible, then you should have got 10,000. Or if one thread is able to do those three mini steps, and the other thread simply waits and does not interfere, right? So it's like one boy is allowed to paint ear, the other boy waits, and the other boy is allowed to paint a nose, and the first boy waits, right? So there is some coordination, some cooperation required, right? So in Java threads also, people have designed ways so that threads can cooperate, threads can um, coordinate among themselves, so that you get right answers. The program is works correctly and reliably. So as each thread is running 5,000 times, there are uh, multiple in many occasions, the interference is happening where individual increments are being lost, uh, and you get answers like this. Okay, so the way we prevent this problem is, this counter has an increment method that is not thread safe. So we actually change the counter method so that the increment method um, becomes thread safe. And the way to do it is, add a synchronized here. So if you add a synchronized statement here, then your program will reliably produce 10,000, right? So you run it many times and you get 10,000, right? So the change was that a method that is changing the shared variable should be a synchronized method. And making a method synchronized is as simple as adding synchronized to it, and the rest of the program is basically unchanged, right? So wherever you have shared memory, shared variable, you need to look at the method that makes changes to it and you know add synchronized. Okay, so that's how we fix the problem related to synchronization. So in the book, you will see that there is a new class that was created called sync counter. The only difference between sync counter and counter is that sync counter's increment method is uh, synchronized. Okay. So let's stop here.